So we got a sense for the size of the boundary layer when you have airflow, sort of standard 1 meter per second airflow over a 2 meter wing. It's only 3 centimeters thick, even at the end of the wing or end of the plate. Let's do the same thing with water. We have a 2 meter plate here, and we're going to flow water over the plate, and the delta, we have a viscous boundary layer for that. We're going to slow the water way down. So we're going to slow it down to 0.1 meters per second. I'll explain why that is later when we understand a little more about turbulence, which we haven't studied yet, but we'll get into that soon. So this is a slower water flow, and we think that that should increase the size of the thickness, boundary layer thickness, because the faster the flow, the thinner the boundary layer. We saw that already. We're going to use our relationship, again, delta over x is equal to 4.92. Reynolds number based on x to the minus 1/2. So that's our relationship for the size of the boundary layer for flow over a flat plate or flow along a wall. And we can plug in all our numbers in here again. So we'll go ahead and use the Reynolds number for the entire length. So we're going to use 2 meters. So we'll put an L there. And then our velocity now is only 0.1 meter per second. We still have the 2 meter length of the wall or the plate. And then we have a viscosity down here, which is the viscosity of water. Now, we know that water is more viscous than air, but this is not the dynamic viscosity, this is the kinematic viscosity. And when you look this up at standard temperature and pressure, you find that the kinematic viscosity for water is actually smaller than it is for air. And that's because, of course, the kinematic viscosity is the regular viscosity divided by the density. And the density of water, of course, is enormous compared to that of air. So the kinematic viscosity is actually an order of magnitude smaller than the kinematic viscosity for air. So that's going to cause the boundary layer to be even smaller for water than it is for air. So when we plug these into our Reynolds numbers, the Reynolds number here is going to be 1.98 times 10 to the fifth. So a similar Reynolds number to what we had before, because the viscosity dropped by a factor of 10, but we also dropped the velocity by a factor of 10. So that gave us a similar Reynolds number in the end. And when we calculate our delta based on that, we get delta equals L times 1.98 times 10 to the fifth, all to the negative 1/2 power, times 4.92. That's just using our formula, which gives you a delta that's equal to 0.011 times that length. And when you calculate that, plug in that 2 meters, we get that the delta for this flow, this water flow over that 2 meter plate, is about 0.022 meters, which of course is about equal to 2.2 centimeters. So really small again, about the same size. Much less than the length of the plate. So we have the plate's 2 meters, and this is like 1/100th of that. So very, very tiny boundary layer there over that plate. So the viscous effects are very tightly confined to the surface of the flow right near the plate. It's a very thin layer. So that's called the viscous boundary layer. And it, generally speaking, is very, very thin, where all the viscosity effects are having an effect on the flow in that very thin layer. It's a very important layer. If it weren't for that layer, the flow would be completely different. For instance, there would be no drag on the plane, or there would be no frictional effects. But all those frictional effects happen in a very, very thin layer, very close to the solid surface in a flow like this.